Hi all, today we discuss theorem 11, second derivative test for local extreme values. So the proof of this theorem is beyond our scope. So we start with the statement. Suppose that f of xy and its first and second partial derivatives are continuous throughout a disk centered at AB. So we are considering a function f of xy and a point in the domain say a comma b, and we consider a disk about this AB, uh, and we have fxab and fyab. That means the partial derivative of f with respect to x at the point AB, partial derivative of f with respect to y at AB, those values will be 0. In this case, we classify this point AB. Okay, this point AB can be classified into three category. One is point of local maximum, local minimum, and saddle points. Okay, so first of all, we evaluate fxx, that is a partial derivative, second order partial derivative of f with respect to x, fyy minus fxy square, and this is denoted by we can easily identify, or you can remember this using this determinant fxx, and this is fyy, that those elements are in the diagonals, and we have xy, fxy and fyx are on the off diagonal. So if you evaluate this determinant, you can get this. Okay, all these values are evaluated at the point AB. When you evaluate these values at the point AB, you can get, there are three possibilities anyway. So if you consider this, then we have three possibilities. The first possibility is this will be equal to 0, and we have this is less than 0, and this quantity is greater than 0. So these are the three exclusive properties, possibilities. Then if this is greater than 0, first of all we can say that if it is equal to 0, then this test is inconclusive. Okay, so we can say that this test is inconclusive. That means we cannot use this test for concluding anything on this local maxima or extreme values. If this is the case, if this is less than 0, this discriminant, this is called discriminant or Hessian. Okay, discriminant or Hessian is less than 0. We can say that that point is saddle point. So in this case, we call this point as saddle point, or otherwise we can say that whenever this quantity is less than 0, with these two conditions, that point satisfies the definition of saddle point. Okay, and in this case we evaluate the other quantity, say fxx. We evaluate partial derivative, second order partial derivative of f with respect to x. Then this has again three possibilities. Okay, so this is equal to 0, then we have greater than 0 and less than 0. When you evaluate this fxx at the point AB, then you have three possibilities. Okay, so one possibility is greater than 0, and this is less than 0. If this is less than 0, we call that value as local maximum value. Okay, local maximum at a comma b, and if this is the case, we can say that local minimum at a comma b. Again, if this is equal to 0, then test is again inconclusive. Okay, we cannot conclude okay, in this case. So these are three important ideas, and we can classify this as a theorem, that is theorem 11. when you evaluate the point AB such that fx and fy will be 0, then evaluate the discriminant or Hessian at AB. Then we have three possibilities. The two of these possibilities can be considered as the conclusion for theorem 11. So if this is greater than 0, then evaluate fxx. Then you can conclude point of local minima and local maxima using the sign of this fxx. And if the discriminant is itself negative, then the point is called saddle point. Or if this is less than 0, it satisfies the definition of saddle point. Okay, so this is what we have observed in theorem 11. Now we are not going to prove this theorem, but we are going to explain this theorem or illustrate this theorem with examples. So this is the first example. Find the local extreme values of the function f of xy equal to xy minus x square minus y square minus 2x minus 2y plus 4. First of all, we have to evaluate the points AB such that at which those points this partial derivative, first order partial derivative, should be 0. So first we evaluate two partial derivatives with respect to x and with respect to y. Then fx will give the expression y minus 2x minus 2. When you equate this to 0, you can get one equation. So this equation can be written as minus 2x plus y equal to 2. So this is the simplest form, and this can be written as x minus 2y equal to 2. When you solve these two equations, you can consider this. These are the system of linear equations, and we can convert it in the matrix form. When you convert it in the matrix form, you can get minus 2, 1, 1, minus 2 times this xy. This is xy, which is equal to 2, 2. Okay, when you evaluate or when you solve these equations, you can use either you can use the matrix form or equating the coefficient. You can easily verify that the x equal to y equal to minus 2. So when you put x equal to minus 2, y equal to minus 2 here, then you will get the identity like this. So this gives the values x equal to y equal to minus 2. Or the other way, you can multiply it with 2 and add up with this equation. Then you can get the value of y itself, y as minus 2. Then substituting that value in one of the equations, you can get the other unknown x. So anyway, when you solve these two equations, you can get x equal to y and x equal to minus 2 and y equal to minus 2. So using these values, we can illustrate example theorem 11. So when you find out the values x equal to minus 2, y equal to minus 2, you can get the point minus 2, minus 2. Then you evaluate fxx this at this point. Okay, what is the derivative of fx with respect to x again? So you need to differentiate this expression with x itself, taking y as a constant. Then this will be 0 and derivative of this will be 0. The only thing is minus 2 here. Then fyy is again minus 2. That is obtained from this expression, and fxy is equal to 1. Okay, so this can be obtained from fx by differentiating fx with respect to y. That means differentiating this expression with respect to y, treating x and other things are constant. So that will be fxy is equal to 1. The other way, you can evaluate fyx. Both are same in this expression. Fyx can be obtained using the fy by taking derivative of fy with respect to x. Both will be same, that will be 1. Then you evaluate fxx fyy minus fxy whole square, that is equal to 3. So from this you can say that this is greater than 0. If this is greater than 0, you can classify this point minus 2 as point of local maxima and point of local minima according to the sign of fxx. But we already evaluated fxx at the point minus 2, so that is a constant value minus 2. So that is negative value. So fxx is always negative. Then we conclude using these two, discriminant or Hessian is greater than 0 and fxx is less than 0. Then this point minus 2 is a point of local maximum, and local maximum value is obtained by evaluating f at this minus 2. Okay, so you substitute this point of maximum minus 2 in this expression, you can evaluate, that is 4 minus 2 square is 4, 4 minus 4, that is 0, and this is 2 times minus 2, that is 4 again, and this is again minus 4, so minus 4 again 0, then we have 4. Sorry, this is minus 2, we didn't evaluate this thing. So here we have 4, and this is minus 4, and this is again minus 4, and this is plus 4, and this is again plus 4 and plus 4. Okay, we have 2 negative 4s and 4 positive 4s, so you can get this value as 8. So we have f of minus 2 is equal to 8. So this illustrates the theorem 11, and we can get this minus 2 as the point of maximum, and the maximum value is 8. The maximum value of this function is 8. Now we discuss example 4. In this example, we consider the function f of xy equal to xy, x times y. First of all, we have to evaluate the points at which the partial derivatives are 0. That is obtained by fx. Fx is the derivative of this expression with respect to x, that is y. Here we treat this y as a constant. So this fx equal to y and fy is equal to x. So the only possible points from this equation is 0, 0. So we will evaluate the behavior of or point of local maximum, minimum, or saddle points using the 0, 0. So first of all, we have to evaluate the discriminant or Hessian. Discriminant is defined as fxx, fyy minus fxy square. Okay. So using the sign of this, we will distinguish these points. So when you evaluate these three things, you can get fxx equal to 0 by taking this expression, by taking the derivative of this expression with respect to x. So that is 0. Similarly, by taking the derivative of this expression with respect to y, that is again 0. F of xy, that is obtained by taking the derivative of this expression with respect to y, that will be 1, or the derivative of this expression with respect to x. So that also gives the same thing, 1. So when you evaluate this, you can get that is minus 1, 0, 0 minus 0 times 0 minus 1, that is minus 1, this is negative. Whenever this discriminant or Hessian is negative, the point is classified as the saddle point. So the point 0, 0 is a saddle point, or we conclude that f of xy equal to x times y has no local extreme values. It has only saddle point. So this example 4 explains the existence of a saddle point. Now we have an interesting problem. Find the absolute maximum and minimum values of this function on the triangular region given in this figure. In the first quadrant bounded by the lines x equal to 0. So this is x equal to 0 along y-axis, and the equation y equal to 0 denotes the x-axis. Okay, and this equation, the equation of this line is y equal to 9 minus x. So we got a region bounded by these three lines. Then that is the shaded region here. Now we have to evaluate the extreme absolute maximum and absolute minima, not the local maximum and minima. So we need to find out the absolute maximum. In order to find the absolute maximum, we need to observe these the points in this region as well as the points in the boundary with fx and fy are 0. First of all, we evaluate those points. So first we consider all the points inside this region, or for the time being we are excluding this boundary points. Then we evaluate fx and fy. Fx gives 2 minus 2x, fy gives 2 minus 2y. By differentiating this, the derivative of this expression with respect to x, taking y as a constant, you can get derivative of 2 is 0, derivative of 2x is 2, that is 2 here, derivative of 2y is 0, derivative of minus x square is minus 2x. Okay, then derivative of minus y square is 0 because the derivative is with respect to x. Similarly, you can evaluate fy. So by solving these two equations, you can evaluate the point xy. From this you can get x equal to 1. From this you can get y is equal to 1. So these two things constitute the point xy is equal to 1, 1. And we evaluate the only possible value is 1, 1. We need to evaluate the extreme value, absolute maximum or absolute minimum. So we are not bothering about the uh, two local maxima and minima. So if we evaluate this function f of 1 1 we evaluate the function at 1 1, that is f of 1 1, that is equal to 4. Okay, now from this expression itself you can evaluate the second derivatives and discriminant all, and you can consider this as point of maxima or minima. So before that we evaluate all the possible values, all the possible extreme values, and we will take the largest of that for getting maximum value, and smallest of that for getting the minimum value. So we are not bothering about the local maximum and local minimum. So we are going to evaluate the absolute maximum and minimum. So in order to find out if you are asked to evaluate the nature of this 1 1, you need to consider fxx. From this, fxx is minus 2. Similarly, fyy, from this expression fyy is minus 2 again, and f of fxy, that is the derivative of this expression with respect to y, so that is 0. Then you can get this is 4. So this value is always greater than 0. Discriminant is always greater than 0. Whenever discriminant is greater than 0 and the second order partial derivative fxx is negative, then this is a point of maximum. So then you can observe the behavior of this point as well. Now we will consider the boundary points. We have three boundaries. Equation of this boundary is y equal to 0, and equation of this boundary is y equal to 9 minus x, and equation of this boundary is x equal to 0. So first we evaluate, in case of boundary points, first we evaluate the segment OA, so that is this segment. In this segment y is 0, then f of xy takes the form, you can neglect all the terms containing y, because y is 0 here. So the expression is 2 plus 2x minus x square. Okay, then this can be treated as a function in x alone. Okay, now we transform this f of xy to a function of x itself. So the problem reduces to evaluate the maximum value of a single variable function gx. In order to evaluate the maximum value of g, we first evaluate g dash x for the critical points. What is g dash x? That is obtained from this expression by taking different derivative with respect to x. So that will give 2 minus 2x. When you equate this to 0, you can get x equal to 1. One possible values x equal to 1 here for this gx. Okay. Now we have the point corresponding x equal to 1. We can evaluate this y. Y is 0. We already taken that y equal to 0. Y equal to 0, then z dash x equal to 1. The corresponding point is 1 comma 0. Okay, so we need to evaluate the function at 1 comma 0, and this boundary has two boundary points, endpoints, that is one is 0 0 and next is 9 comma 0. So we need to evaluate only these 3 points. Okay, at these 3 points, when you evaluate f at these 3 points, you can get f of 1 0 equal to y is 0 here, so you need to evaluate this expression, that is 2 plus 2 minus 1. Okay, so that is 2 plus 2 minus 1, that is equal to 3. So that is the value of f at this. The point f of at the point 0 0, the value of f is 2, and at the point 9 0, the value of this function is you can evaluate it from this itself, because y is 0 here, that is 2 plus 18 minus 81. 2 plus 18 minus 81, so that will give minus 61. So these are the only possible values or possible candidates for absolute maximum or minimum. Okay, this is the first case. In the second case, we observe the segment OB, that is x equal to 0. Whenever x equal to 0, this reduces to f of xy. F of xy reduces to f of 0 comma y. That gives 2 plus 2y minus y square. For the similar argument, we can get the points. We can take it as h of some y. and evaluate h dash y. From that equal to 0, then you can get y is equal to, from that expression you can get the value of y is 1. Okay, and this is for x equal to 0, then y equal to 1 implies the point, corresponding point xy is 0 comma 1. So the only possible point is 0 comma 1 along with the endpoints. What are the endpoints? Endpoint is 1, endpoint is 0 0, so that is already discussed, and another thing is 0 comma 9. So you can evaluate two points here, 1 0 and 0 9. Then f of 0 1, that will give 2, that will give 3 again by putting y equal to 1 in this expression, and f of 0 9 is again minus 61 by evaluating this expression by putting y is equal to 9, so that is again minus 61, and f of 0 0 is again 2, so that is already discussed in this session. So these are two candidates for absolute maximum and minimum. So it remains to consider this boundary. We already discussed two endpoints here, so we need to consider all the points on this boundary except 0 9 and 90, and that is obtained by putting y equal to 9 minus x in the expression of f of xy. So that will give this expression. This is the expression for f of xy. By putting y is equal to, this is y is equal to 9 minus x here, and y square is equal to 9 minus x whole square. Then simplifying this, you can get minus 61 plus 18x minus 2x square. Okay, then by taking this contains only x, so you can consider this as some g1x. This is a function of x alone. Then find the maximum of or extreme values of this g1x. By first of all, we have to evaluate g prime x. Okay, g prime x is obtained by differentiating this expression. Differentiating this expression with respect to x, then you can get g dash x equal to 18 minus 4x. By equating this to 0, you can get x equal to 18 by 4, that is equal to 9 by 2. So there is only one candidate, x equal to 9 by 2. The corresponding y, that is obtained from this expression, y is equal to 9 minus x, that is 9 minus 9 by 2. Okay, 9 minus 9 by 2 is again 9 by 2. That is half of the 9 subtracted from 9 again. So that is again the half of 9. So y is again 9 by 2. Then the corresponding point is x comma y is x is 9 by 2 and y is 9 by 2. The corresponding point is 9 by 2 comma 9 by 2. And evaluate f of xy, that is f of this expression or this expression at the point 9 by 2 9 by 2. By substituting 9 by 2 here and 9 by 2 here, you can get the value is minus 41 by 2. So the only candidate here is f of 9 by 2 9 by 2. So that value is minus 41 by 2. So what are all the points, all the values of f of xy? So f of xy takes the values 3, 2, minus 61, and we have minus 41 by 2 in the boundary points. And we have considered this in the interior points, that value is 1, 4, that is f of 1, 1. So among these are the only possible values for extreme value or extreme point of extreme values. So among this, you can say that this is the largest value. So this is what we call the absolute maximum. Okay, and among this is the lowest. Okay, and this is the largest. Okay, this is the largest and this is the lowest. Then this is absolute maximum and this is absolute minimum. Okay, now we conclude. From this we conclude 4 is the maximum value of f, and it is assumed at the point 1 1, and minus 61 is the point of minimum, absolute minimum, and it assumed at the point 0 9 or 9 0. At both of these points, the f takes on the value minus 61. Okay, so this is explained example 5. Now we have example 6. This is an application problem. So this is a worked out problem. So try to solve this problem and submit it as assignment. Submit it for assignment. If you have any doubt in this example 6, please free to contact me, and we will arrange a Google Meet to explain this. Otherwise, you can write out all this problem and submit it as an assignment. Thank you. So this completes section 14.7. The next class we will discuss section 14.8.